Good day, dear students and all the listeners. Today's topic is the second law of thermodynamics. To this point, we have focused our attention on the first law of thermodynamics, which requires that energy be conserved during a process. In this chapter, we introduce the second law of thermodynamics, which asserts that the process occurs in a certain direction that energy has quality as well as quantity. A process cannot take place unless it satisfies both the first and the second laws of thermodynamics. It is common experience that a cup of hot coffee left in a cool room eventually cools off. This process satisfies the first law of thermodynamics, since the amount of energy lost by the coffee is equal to the amount of gained by the surrounding air. The first law dictates that the amount of electric energy supplied to the resistance wires to be equal to the amount of energy transferred to the room air as heat. Now let us attempt to reverse this process. It will come as no surprise that transferring some heat to the wires does not cause an equivalent amount of electric energy to be generated in wires. The paddle wheel rotates as the mass falls and steers the fluid within an insulated container. As a result, the potential energy of the mass decreases and the internal energy of the fluid increases in accordance with the conservation of energy principle. However, the reverse process, raising the mass by transferring heat from fluid to the paddle wheel, does not occur in nature, although doing so would not violate the first law of thermodynamics. Processes occur in a certain direction and not in a reverse direction. A process must satisfy both the first and the second laws of thermodynamics to proceed. It is clear from these arguments that processes proceed in a certain direction and not in a reverse direction. The first law places no restriction on the direction of the process, but satisfying the first law does not ensure that the process can actually occur. This inadequacy of the first law to identify whether a process can take place is remedied by the introducing another general principle, the second law of thermodynamics. We show later in this chapter that the reverse process discussed above violates the second law of thermodynamics. This violation is easily detected with the help of a property called entropy, defined in previous lectures. A process cannot occur unless it satisfies both the first and the second laws of thermodynamics. The use of the second law of thermodynamics is not limited to identifying the direction of the process. The second law also asserts that energy has quality as well as quantity. The first law is concerned with the quantity of energy and the transformation of energy from one form to another with no regards to its quality. Preserving the quality of energy is a major concern to engineers, and the second law provides the necessary means to determine the quality as well as the degree of degradation of energy during process. For example, a reservoir that supplies energy in the form of heat is called source, and one that absorbs called sink. Thermal energy reservoirs are often referred to as heat reservoirs since they supply or absorb energy in the form of heat. As pointed out earlier, work can easily be converted to another forms of energy, but converting other forms of energy to work is not that easy. The mechanical work done by the shaft shown in figures presented in this presentation, for example, is first converted to the internal energy of the water. This energy may then leave the water as heat. We know from experience that any attempt to reverse this process will fail. That is, transferring heat to the water does not cause the shaft to rotate. From this and other observations, we conclude that work can be converted to heat directly and completely. But converting heat to work requires the use of some special devices. These devices are called heat engines. Heat engines differ considerably from one another, but all can be characterized by the following. They receive heat from high temperature source, they convert part of this heat to work, they reject the remaining waste heat to a low temperature sink. They operate on a cycle. Heat engines and other cyclic devices usually involve fluid to and from which heat is transferred while undergoing a cycle. This fluid is called the working fluid. The work-producing device that best fits into the definition of a heat engine is steam power plant, which is an external combustion engine. That is, combustion takes place outside the engine, and the thermal energy released during this process is transferred to the steam as heat. The schematic of a basic steam power plant is shown in the following in this picture. We can see that there is a boiler, a turbine, a condenser, and a pump. The water is pumped to the needed pressure, then the water is boiled, and the vapor or steam goes through the turbine, then goes to the condenser. The condenser is called as the energy sink, and the boiler is the source of a heat source. Thermal efficiency. The inequation above, Q out represents the magnitude of the energy wasted in order to complete the cycle. But Q out is never zero, thus the net network over the output of the heat engine is always less than the amount of heat input. That is, only part of the heat transferred to the heat engine is converted to work. The fraction of the heat input that is converted to network outputs is a measure of the performance of a heat engine, and it's called thermal efficiency. Cyclic devices of practical interest such as heat engines, refrigerators, and heat pumps operate between the high temperature medium and the low temperature medium at temperature TL. To bring uniformity to the treatment of heat engines, refrigerators, and heat pumps, we define these two quantities as following. The efficiency is the amount of energy that we get useful energy, and the amount of energy that is consumed to produce this useful energy. Generally, the efficiency of the heat engines are not higher than the 40%, 20%. We all know from experience that the heat is transferred in the direction of the decreasing temperature, that is, from high temperature mediums to low temperature ones. This heat transfer process occurs in nature without requiring any devices. The reverse process, however, cannot occur by itself. The transfer of heat from low temperature mediums to high temperature mediums, one requires special devices called refrigerators. Thus, these all devices are simply working by the principle of the first and the second laws of thermodynamics. The first law dictates that the conservation of energy. It means that the total energy are transferred in different types of energy: heat, electricity, chemical energy, and other types. And the second one dictates the direction of the movement. For example, if you are using heat engine, some part of the heat is transferred to the mechanical, and other types is going through like heat. So thus explaining the second law of thermodynamics. Thank you very much for your attention. That's it.